Okay, so first, thank you for the opportunity of talking here. It's the first time for me in Lisbon. I'm very happy to be here. I will talk about this topic. It's based on our work, which is also currently ongoing, and follow up with Marco Melis, which was here for a couple of months, and Croft and Paolo Pani. So let me start. Okay, we all know. We all know compact objects when they collide, when they merge, emit gravitational wave. And the typical anatomy of a gravitational wave, okay, is well known. We know we can divide it in three parts. We have a spiral, a merger, and a ringdown. In the spiral, we have the two objects orbiting around each other. In the merger, we have the moment of the collision between the two. And finally, we have the ringdown, which is the system relaxing towards its final configuration. Now, often the ringdown stage is studied using, as you well know, perturbations theory. So we consider a final object and we add a perturbation on top of it to study how it responds to perturbation. And this gives already an estimate of what we should see at the end of this process. Now, in the case of two black holes in general relativity, we expect a standard ringdown of this wave when we see the semi-log scale. So we expect to see an oscillation which is exponentially damped with this simple behavior. However, if we are not considering black holes or we are not considering general relativity, this picture might change, meaning that in turn, an eventual deviation from this very simple profile will signal either that we are looking at a different object with respect to a simple black hole, or that the underlying theory driving this system is not GR. So among the possible modifications, we can introduce one of the most famous is echoes. And the idea is the following. Let's go step by step. Let's consider, for example, the case of a black hole. We have an horizon, which is a black dashed line here, if we consider the final stage of a collision, and we add an effective potential for gravitational perturbation. Now, let's suppose we add a perturbation of the gravitational field on top of it, which represents actually the system relaxing to its final state. What you expect is that part of this perturbation will propagate to the right, part of this perturbation will propagate to the left. The part going to the right is the one we actually observe at spatial infinity. The other part enters the horizon and essentially disappears from our knowledge. It becomes casually disconnected. So more or less, what you expect to see is this one. Part, which is the prompt ring that we observe, goes to infinity, and then the other gets absorbed by the rest. But if instead, as in the case of exotic compact object, we have, instead of an horizon, we have a reflective surface, what happens is that if we add a perturbation, part will propagate to the right, as in the black hole case, which is the prompt ring down we observe. The ingoing part gets reflected by the exotic compact object and then travels outwards again. But then it will scatter off this potential barrier formed by the effective potential. Part will be transmitted through the barrier, part will be reflected, undergoing another reflection to the surface of the exotic compact object, and so on, producing echoing signals that will be observed in subsequent wave packets, essentially. So, for example, this is a situation in which a different object introduces a different phenomenology. Now, to produce echoes, this is a qualitative picture, of course, we need a cavity-like structure this way. So we need a cavity, in this case, is formed by the surface of the compact object and the effective potential, in which the perturbation can reside for a long time and undergo this statistical scatter and produce this echoing signal. What is interesting is that a couple of years ago, it has been noticed that a similar phenomenology can also happen for black holes, but in a modified theory of gravity, actually an essential general relativity, which is Einstein-Maxwell-scalar. So let's go step by step. Einstein-Maxwell-scalar is governed by the action that you see on the screen. Essentially, we have the Einstein liberté for standard general relativity, and modifications come into the matter term. So we have a real scalar field and the electromagnetic field, which is non-minimally coupled to the metric via coupling function f of phi. Now, interestingly, for some specific choices of the coupling function, for example, an exponential or a quadratic coupling function, we have the phenomenon of spontaneous scalarization. So we have additional black hole solution. Let's quickly see how it goes. Very briefly, the equation for the scalar field given by the action I've shown you before is this one that you see here. Now, interestingly, if there are some choices of the coupling function such that there is a constant profile for the scalar field over which the derivative of the coupling is 0, then this constant configuration satisfies automatically this equation. The scalar field doesn't enter anymore in the matter term of in the stress energy tensor, basically. So we have general relativity, the Einstein's equation, plus a constant profile of the scalar field. So we have a Rice-Nostrom black hole solution, an electric, or a Kerr-Newman solution if you consider rotating configurations. Now, if we perturb this configuration, we have a perturbation on top of it, we obtain an equation for the perturbation which has this form. So it's a Klein-Gordon equation, like, where the effective mass square is given by this term here. And depending on the choice of the coupling function, it is possible that this effective mass square becomes negative. And if this is the case, it might be possible that the GR solution, so the Rice-Nostrom black hole solution in the case of spherical symmetry, is subject to a tachyonic instability, so instability given by a negative effective mass square. In this case, what happens? We know that the scalar-free solution, so the Rice-Nostrom black hole solution, is unstable, but the theory also admits other black hole solutions with a non-trivial profile of the scalar field outside them. So they are called scalarized solutions because they have the non-trivial profile of the scalar field. And what can happen is that if we start from a Rice-Nostrom black hole solution and we add a perturbation, the system transits spontaneously towards one of these Hayry configuration with a non-trivial profile of the scalar field in a process which is not a spontaneous scalarization. But in order for this to happen, we need that this condition is true, so Rice-Nostrom black hole solution is actually a solution of the configuration, and that the effective mass square is negative. Now, interestingly, let's see how is this. Yes. Yeah.
For some potential some of the magnetic field.
Yes.
That's modified equation.
Yes, it's coming, but well, actually, the equation is very, very similar to the. I can write it down. Yeah, the equation from the electromagnetic field is basically this. So it's essentially the same as Maxwell equation with the coupling function here. Right. But if actually with the choices I got before, the condition is that if phi equals 0, then equal to 1, so the scalar-free solution reduces to Maxwell's equation. Yeah. Okay. Okay, so how are these solutions made? Okay, this is an example for the exponential coupling. This is a Schwarzschild ansatz for the metric. We have a radial profile of the scalar field. We are considering a symmetric stationary configuration. And we can see, okay, this is the exponential coupling function with a coupling constant alpha equal 20, which is dimensionless, and a Charles-Mass ratio 0.7. We can see that there is a non-trivial profile of the scalar field, this red line, and the Misner-Sharp mass is not constant. So, and yes, and then we have the other metric functions. And what about the domain of existence of this configuration? Now, here I'm considering the other coupling, but it's essentially the same because this is expansion of this second order. The domain is essentially the same. On the x-axis here, we have the coupling constant, on the y-axis, the Charles-Mass ratio. And what we see, there are two lines. The blue one is called existence line, and this is the line below which no scalarized black hole solution exists. So scalarized black hole solution only exists above this line. Below this, we only have the Rice-Nostrom black hole solution. Above this, we have the scalarized black hole solution bifurcates from the Rice-Nostrom black hole solution, and they extend up to the critical line, the red line here, which is a configuration which is likely extremal in the sense that the mass and the charge remains finite. The areal radius goes to 0, so the horizon area shrinks to 0, and the Kretschmann scalar diverges. So these are likely singular configuration. But interestingly, this solution can extend over the Charles-Mass ratio equal 1. This is not possible for a Rice-Nostrom black hole solution because in order to have in the Rice-Nostrom solution, in order to have horizons, we need the Charles-Mass ratio to be smaller than 1. Otherwise, we would not have horizons and we have a naked singularity. So for bicosmic censorship, we know that the Charles-Mass ratio of a right-dimensional black hole solution should theoretically be below 1. This is not the case for scalarized black hole solution, and the Charles-Mass ratio can extend above 1. Now, let's go to radial perturbation of this solution, since our final goal is to study the possibility of forming echoes in this configuration. I will show that this is technically possible. So if we consider that we start with linear radial perturbation, we consider Schwarzschild ansatz for the metric, and we plug in the metric function the electromagnetic potential and the scalar field, essentially the static and spherical symmetric solution plus some perturbation. Then by manipulating the field equation, we managed to write all the perturbation equation in one master equation for essentially psi, which is a definition of the scalar perturbation, and R star is the tortoise coordinate. So all this perturbation through essentially manipulation of the equation gets encoded in this one equation, which is a wave-like equation with an effective potential. So whether we will be able to see echoes or not depends on the form of the effective potential. And what has been found recently, and this is what is interesting, is that for some specific choices of the Charles-Mass ratio and the coupling constant of the solution, we get cavity-like structures in the effective potential. So this is the exponential coupling function, is the one I will consider for the rest of the talk. And for small values of the coupling constant, very small, and for close to extremal value of the Charles-Mass ratio, we obtain that the effective potential possesses cavity-like structures, which are suitable for echo generation. So here we can have the phenomenology I was described in the second slide, in which radiation bounces back and forth and produces echo. Yes?
Sorry, in this one part, are you considering the scalar perturbation decoupling, or the decoupling perturbation of electromagnetic field?
No, this should be all coupled.
It's all coupled?
Yeah.
Okay, yeah, because from the question I thought you would before.
Yeah.
This psi.
Yeah. Yes, but this is not just the equation for the scalar field. It is a redefinition of all the equations of the field equations.
Okay, no, because psi is like by 1 times r, right?
Yeah. Yeah.
So you fixate the electromagnetic field and you perturb it with the scalar field.
No, actually, we are adding all the perturbations, so we are perturbing everything.
Also the electromagnetic.
Yeah,
okay.
yeah, it's here.
But you only have one equation because it's radial perturbation.
Yes. Yes, it's radial perturbation.
Okay.
It's just radial perturbations.
Okay.
Yeah.
Okay, yeah, I would.
Yeah. Later we will consider also axial perturbation, and we will have a coupled system.
Okay.
Yeah. Okay, so we have these cavities that are suitable for echo generation. And so we will like to investigate whether this is the case, whether there are long-lived modes and echoes. But before going into that, let me stress one point, because now a possible question would be, okay, but you are considering a theory which is unmotivated. You are considering a tiny region of the parameter space for scalarized solutions, which we do not have a hint of detection of this thing, and you're also considering overcharged configuration while we know that black holes should be neutral. So why should we consider that? Well, the point is that we shouldn't. We just the logic is reversed. So the question is not whether we can put constraint on this model based on the signal we observe, because this is not likely to happen. But the point is the reverse. So given a theory that provides this form of effective potential, what phenomenology do we expect? What will the impact of this configuration be on the gravitational wave signal? And in this respect, Einstein-Maxwell-scalar is a wonderful toy model, because it's a small modification with respect to general relativity. The equations are super simple. They are well posed. Basically, it's just general relativity, but provides a phenomenology which is actually substantially different. We have scalarized solution. We have multiple peaks of the effective potential. So the idea is really to see what we can learn from this kind of modification, rather than taking this too seriously and say whether we can detect this kind and whether we can constrain this kind of configuration. So okay, let's now go to the perturbations equation. The master equation we should solve, at least for radial perturbations, this one, and we can use two methods. We can go in the frequency domain or in the time domain, depending on which side of the Fourier transform we want to be. So we actually use both strategies, because in order to see whether there are echoes, we should go in the time domain, but to compute the quasi-normal frequency, we need to be in the frequency domain. So for the frequency domain, the idea is just we express the scalar perturbation in terms of its Fourier transform. We plug into our equations, and we search for the value of omega that solve these equations. Well, in the time domain, the general idea is that we cast this equation as a system of first-order differential equation in time. We provide the initial data for the scalar perturbation, we evolve it in time numerically, and we extract the behavior of the solution at a given radius to see whether we are actually seeing those. So let's start with the frequency domain computation. The equation is this one in the frequency domain. In order to solve this, we should impose boundary condition on both sides. So at the horizon, we have this polynomial expansion here, where this table of coefficient can be fixed recursively by solving this, by putting this equation. We just need to fix the first coefficient, but by linearity, this is trivial. And at infinity, we have a superposition of an ingoing and an outgoing wave. But since we want to compute quasi-normal mode, we only want the solution to be an outgoing wave at infinity, so we get rid of the ingoing part, and we require that we only have the outgoing part. So we require that the ingoing part is 0. So by a shooting procedure, by an iterative procedure in which we solve the equation iteratively and update the value of omega at each iteration, we find the value of the complex frequency omega and the solution that leads to that satisfies both boundary conditions. By performing this procedure, we arrive to these quasi-normal modes. Here we have on the top panel the case alpha 0.5 and on the bottom 0.6. The right plots are the real part of the quasi-normal frequencies, and the right part is the imaginary. The right plots are the imaginary part of the quasi-normal frequencies. Different colors are different overtones, and on the x-axis we have the Charles-Mass ratio. We start from 1, so we are really looking into this configuration close to extremality. And what is interesting here is that here, for example, in the imaginary part, we see that the imaginary part of the frequency of the fundamental node is considerably smaller than the other one. But as the Charles-Mass ratio increases, at some point, the imaginary part drops, meaning that and becomes comparable to the fundamental node. So the damping time increases in the last configuration close to extremality, and we have the potential of seeing echoes because they can interact with each other. So this is the structure of quasi-normal modes. But in order to understand whether we actually see echoes, we need to go to the time domain. So now I have a small slides on how time domain methods work. I don't know how much for the audience this will be useful, so I tend to go real quick. So the idea is to solve this couple equation of first order, providing an initial profile of psi perturbation and psi dot, which is the time domain. We want to provide an initial data, but we cannot feed the initial data directly into the equation because we need to solve it on a computer. So we apply a discretization procedure. And essentially what we want to do is discretize the system and select a set of points, of discrete points on the radial coordinate. And we evaluate the initial data on all these points. Now, in memory, we will actually store only the value of the fields at this point. We don't have the continuous profile anymore. And we essentially discretize the system in the sense that we can write it as a system of differential equations for each of the grid points, which we can now solve as ordinary differential equations. The only point is evaluating the right-hand side. These terms are easy to evaluate because they just contain the field, and this is the same. But this contains derivatives, so we need to find a way to compute derivatives. And the idea is that we use finite different formulas. So we essentially use the grid points adjacent to a given grid point to get an estimate of the derivative to a certain degree of accuracy. So there are formulas we use adjacent grid point to the CI to compute derivatives. In this way, we can evaluate the right-hand sides. So we have a set of differential equation in time for each of the grid points, which we can solve via a method for ordinary differential equations, such as the Runge-Kutta method. So at each iteration, we evaluate the right-hand side, we apply the integrator, so the Runge-Kutta method, and we proceed iteratively. Over time, this will lead to an evolution of the discretized system, which hopefully will represent a solution of the continuous equation given the initial data we gave. So this is generically the structure. And what we did is we solved the equation I showed you before, so only considering perturbation with the effective potential for scalarized configurations, starting from a Gaussian wave packet of the perturbation, and we recorded the value of the scalar perturbation at a given radial point. Here we see the results. Again, upper panel is alpha 0.5, lower panel is alpha 0.6. And left plots are in linear scale and right plot in the log scale. Here, the black line is the actual simulation data, while the red line is a fit of the late time behavior of the perturbation using the quasi-normal modes computed in the frequency domain. So here we did not fit for the frequency. We imposed that the frequency are the same when computed in the frequency domain, and we fitted for amplitude and phases of the wave. And we see that this reproduces very well the behavior in time. So meaning this is a sanity check if you want for the coefficient we computed. And also we can see some echoing behavior here. Now one could say, okay, but it is an echoing behavior in the sense that also quasi-normal mode reproduce this. But it's very tiny with respect to what we expect to see, for example, for exotic combat objects. But this is more or less the point. What is the impact of the scalar potential we have on the late time signal? And we can see there are echoes, but they are tiny. And this is due to the fact that instead of having a reflective surface that reflects everything that gets through it, here we have a potential barrier. So we have two maxima with a minimum in between, and the boundary of the cavity in the effective potential allow for a leakage of radiation through the inner part, so towards the black hole. So part of radiation leaks towards the horizon. This energy is removed, and this decreases the strength of the echoes we see. So still, the cavity produces echoes, but they are small. Okay, this is for spherical perturbation. We also consider axial quasi-normal modes. The equation for perturbation is the one you see here. Here we have the coupling between electromagnetic and gravitational perturbation. U represents the electromagnetic perturbation, H represents the gravitational perturbation. And now there is a difference with respect to Reise-Nostrom case. In Reise-Nostrom case, we can disentangle the perturbation, so we can redefine the perturbation variables in such a way that the equations are decoupled. One of these new degree of freedom will contain more of a perturbation of the gravitational field and less of the electromagnetic field, so it is gravitationally led, and the other the opposite, so will contain mainly the electromagnetic perturbation, so is electromagnetically led. This is not possible in this case. Apparently, as far as we understood, this is not possible. It is not possible to decouple the perturbation, so they are inherently coupled. And when we computed the quasi-normal mode, we classify them as electromagnetic led or gravitationally led based on how they connect to the Reise-Nostrom black hole. So if these modes are connected to the electromagnetic led modes of the Reise-Nostrom solution, we call them electromagnetically led, otherwise we call them gravitationally led. So these are the quasi-normal modes. We also perform simulations in the time domain. For example, we consider this configuration here, L equal to modes. The effective potentials also for axial perturbations. Here are the electromagnetic, the mixed term, and the gravitational. They all possess this cavity-like structure, so in principle they are suitable for echo generation. And if we simulate in time evolution of perturbations, we obtain this behavior. Here we considered different values of the amplitude of the two perturbations. So In the upper panel, we have a configuration in which the amplitude of the perturbation for the electromagnetic field is way larger than that of the gravitational field. On the bottom panel, we have the case in which the gravitational perturbation is way larger than the electromagnetic one, and essentially the equal case, so equal amplitude case. Now, here the phenomenon is very complicated because the modes are coupled. Also, for example, the mixing term has a potential cavity which is very, very tiny, but it's not so much pronounced. Still, we see some sort of echoing behavior, but interestingly, this happens only for the subdominant part of the perturbation. So if the electromagnetic perturbation is subdominant with respect to the gravitational, it produces the stronger echoes, and the other way around in the opposite case. So this is hard to interpret actually, but still, this is what would solve this. Now, all of these were done at the linear level. So we know there are spherically symmetric perturbations, they produce echoes, also axial perturbation kind of produce echoes. But then the question is, if we want to see this in a binary black hole simulation, in a binary black hole merger, we should take into account the back reaction of the perturbation. So do nonlinearities, does the back reaction of the perturbation on the magic spoil the presence of echoes? And to answer this question, the first thing we do was to perform nonlinear simulations in spherical symmetry. So the setup is conceptually the same as in the axial case. We have a central black hole and a perturbation of the scalar field, which we collapse towards the black hole. But this time, we solve the full system of field equations. We solve the full field equation, we consider all the nonlinearities, and we see what happens if we see echoes or not. Now, very briefly to discuss how these simulations are made, we choose an answer for the metric. We use fine-Lebesgue-Goultran coordinates, which are horizon penetrating, so we can find the evolution inside. Here, R is the areal radius. We define a bunch of auxiliary variables for the scalar field. And for the electromagnetic field, the only non-vanishing component is FTR, or FRT, which can be written in terms of the electromagnetic. Now, since we are considering an actual black hole, there are some difficulties compared to the linear case. So let's consider, for example, here the profile of the scalar field in terms of the areal range. Here, since the coordinates are horizon penetrating, at some position we will have the horizon. But at the center we have the singularity, because here the Kretschmann-Scalar diverges. So we likely have a curvature singularity. And we cannot perform the evolution till the singularity, because here quantities are diverging and numerical methods cannot handle this. So we implement an excision strategy, and we remove from the domain of integration all this region here. And we integrate the equation only starting from the black line towards infinity. Now, the handling of boundary conditions and essentially the evolution equation at the excision boundary introduces numerical error in the simulation. Now, if the excision boundary is located inside the horizon, information of this error cannot propagate towards infinity, so we are safe. Since we want to observe the phenomenology of echoes is what's happening outside the black hole, this is not spoiled by eventual error happening here. But we should make sure that there is a sufficient amount of grid points between the excision boundary and the horizon radius. But this in this case is a problem because we are considering solutions which are close to extremality. So the horizon areal radius is very, very small. And if we set a uniform grid step, so if we discretize the radial coordinate with uniform spacing, then we will need to use a very small grid step in order to solve this part. And we will be forced to use the same resolution also far away from the black hole where this is not needed, and it will be a huge waste of computational resources. So to handle this, what we did is essentially we implemented a fisheye coordinate transformation. So we redefined the radial coordinate. We introduced a radial coordinate small r, where here capital R is the areal radius, but given a fixed function, we decided once. And it's assigned with a specific logic. So let's say the profile of the scalar field is the one that you see examples profile of this way in terms of the coordinate radius. If we impose a uniform scheme in the coordinate radius r, depending on the choice of the transformation, the Fisher transformation, capital R as a function of small r, we will have a non-uniform resolution in the areal radius. So the idea is to implement a specific choice of the transformation capital R so that we have a high resolution in the areal radius in the region close to the horizon where we need high resolution and a smaller resolution outside. Once done this, essentially the path is the same as in the linear case. We need to perform the evolution with the method of light, but now keeping solving for all these variables. So we replace these answers in the field equation. We obtain an equation, a system of evolution equations and constraints. We provide some initial data. We evolve for all these variables. So the setup is, we constructed this. We have a central black hole, a perturbation. We simulate the collapse, and here are the results that we obtain. In the case of a small amplitude, we obtain exactly the same phenomenology as in the linear case, which is to be expected. Again, here the blue line is the numerical evolution, and the dashed line, the orange dashed line, is the fit with the quasi-normal modes computed in the frequency domain. So still the fit works well in describing the behavior, and we still see what is the same behavior as in the previous one. If we now increase the amplitude to this value, we still see some echoes. Now, the amplitude is small, so the mass of the black hole does not increase too much. Also, we cannot increase the mass of the black hole too much, otherwise the Charles-Mass ratio will drop and we exit the region in which this level of potential exists. But still, in this simulation, the horizon areal radius grows by a factor of 5.7. So this means that we are well in the nonlinear regime. The back reaction is substantial, and we still see an echoing behavior even at the nonlinear level. Okay, so, but this is just a hint. This is a scalar perturbation. We want to see what happens in binary black hole simulations. So we are now starting considering, and this is work in progress, a collision scenario. In particular, we would like to simulate the head-on collision between two black holes in this case. Now, here, this is a huge problem because one of the nonlinear simulation I've showed you before lasts, well, it takes order of 100 to 1,000 core hours, and is a spherical symmetric simulation, so there is just one dimension. When we go to 3 dimensions to simulate a collision, the amount of computational resources explodes, and you need essentially a supercomputer. Now, the setup of a head-on collision helps a lot for 2 reasons. One is the fact that the simulation time is shorter because the process is shorter. We don't have the spiral. So the simulation time is cut. But the other is symmetry. So we can try to reduce the computational cost by taking advantage of symmetry. A first strategy will be cutting the simulation domain. So since the setup is axially symmetric, we could, for example, consider a quadrant of the entire system. And this will cut the simulation cost by a factor 4. But if we consider equal black holes, we can even be more extreme and consider an octant of the symmetry, because by reflection, you get the other side. We tried this, but still it's totally unfeasible. Even test simulation lasts, I think, an estimate went to 100,000 or million core hours. It's crazy, because the horizon is very small. These are close to extremal configuration. So we needed to resort to another strategy, which is taking fully advantage of axial symmetry and using the cartoon method. So taking just one two-dimensional slice of the simulation. So how does cartoon work? Basically, we are taking just an XY plane, a half a plane of the simulation domain, and we perform the simulation on this plane, but keeping a Cartesian approach. So we are not using cylindric coordinates, but we are really using Cartesian coordinates on this two-dimensional slice. What is the problem here? Let's say we have, this is a side view of the grid. Let's say we are watching the grid from this side. So we have the x-axis, which is this one, the y-axis, which is this one, and the perpendicular axis is the z-axis. The point is, I can compute numeric derivative with respect to the x-coordinate because I have adjacent point along the x-coordinate. I can do the same for the y-coordinate, but what can I do for the z-coordinate? I would, in principle, need points that are orthogonal to the plane, which are not in the domain of integration. Now, thanks to axial symmetry, in principle, we can imagine that a rotated plane, a simulation grid, will have all the grid functions which are essentially the same on the rotated grid points. But still, we need really the derivative with respect to z. So we will not like to follow the rotation. We really need to compute the derivative by going in the orthogonal direction. So what can we do? Well, the idea is that if we impose that the derivative of all tensors with respect to the generator of the rotation, if we impose that the lead derivative of all tensors with respect to the generator are 0, we can find a way to express the derivative with respect to z in terms of the other one. To be more concrete, let's say we have a vector. The lead derivative with respect to the generator of rotation is given by this expression here. If we evaluate it on the xy plane, so we put z equal to 0, we obtain an expression for the derivative with respect to z of all the components of the vector in terms of other terms we can compute. So with this, we are then able to simulate, to write the code to simulate the head-on collision. And this is essentially what we did. We are working with Giarciombo. This is a part actually done almost entirely by Robin, Robin Croft, which inherited a private branch of the Giarciombo code from Tamara, in which basically we have the two-dimensional period, whatever. Robin implemented the field equation and the condition for derivatives. He also implemented, a superposition of the initial configuration, because then the problem is how we construct initial data. What we are currently doing is taking two spherically symmetric scalarized solutions and superposing them. They will be attracted by each other and they will merge at some point. But this creates problem because GR is nonlinear, so, and also Einstein-Maxwell-scalar, of course. So a superposition of solution is not a solution. So what we are actually seeing, and this is the point we are stuck right now, is that the two black holes begin with a superposition configuration. There are some errors due to superposition, but they can be done the way due to the scheme we are using. But when they get close to each other, this superposition error grows considerably and essentially spoils completely the simulation. Now we are also, actually Robin again is implementing a boost of the initial data that should help in this because essentially due to length contraction and due to the fact that you're adding momentum, so you can put black holes farther apart. But currently the stage is this. This is a simulation we run. Basically up to this point, the simulation is consistent across different levels of resolutions. Here I will show you the F-squared terms, so the strength of the electromagnetic field. And this is really our simulation domain. Here, in light gray, you see the grid structure, and you see boxes which represents AMR boxes. So Giarciombo has the capability of adding layers of the grid with larger resolution where it is needed. So it adds these boxes of grids with larger resolution, detecting where it is needed and following the black holes. If we go, essentially, we remove all of this and we unwind the symmetry, we get this situation here, where still you can see that there is a repulsion of the electric field because this asymmetric profile of the field strength. But currently, due to superposition error, we are not yet able to go through fully merger in a consistent way. We are working through that and we'll see where it goes. So with that, I conclude just a summary. So in Einstein-Maxwell-scalar theory, we see that there are Haley black hole solutions with a cavity-like structure of the effective potential that are suitable for echo generation. We computed the quasi-normal mode in the frequency domain and performed simulations in the time domain, and we actually see echoes which are tiny due to the structure of the effective potential, but they are there, and they appear also when the dynamics are in a linear regime, so they are not spoiled by the back reaction of the perturbation to the magic, and you're working to simulate the head-on collision to see, because this is the big next question. So we know that nonlinearities do not spoil, are likely not to spoil, at least in the spherical symmetry case, the presence of echoes, but the dynamics in a head-on collision on the binary major is much, much richer. So we should see whether there are other dynamical effects which can spoil the presence of echoes. And with that, I conclude. I thank you once again for the opportunity. questions?
Yes, so just to be clear, in the trombone electrons, there you've moved away from backward excision. That's like the standard moving puncture.
Yes, this is something.
Standard moving puncture.
Yes, but actually production of initial data is not as easy, in the sense that
You're not solving strength.
yes, we solve the constraints, we construct spherical symmetric black hole solutions in an isolation, which are numerically constructed, and then we superimpose them. But still, the construction of initial data is not trivial, because essentially you cannot use, in this case, standard, for example, pre-collapsed graphs, because this does not admit a solution. Essentially, there are some quantities going to zero, and they are not suitable for simulation. So in this case, we should do a gauge tuning to find the correct gauge that gives us the initial data. Then we feed into GR Chombo, which uses standard moving puncture approach and CC4, and then with 1+ log slicing and standard approaches, we get the.
I have one more question.
Yeah.
I'm cheap, and I wonder if you couldn't do something easier without symmetry when doing a head-on collision that you say is really expensive. Did you try just evolving in the 3D code or in the axisymmetric code, like the same configuration that you did in the spherical code, and then just putting in an axisymmetric perturbation in that? Can you reproduce the results of the spherical results? Because then you could already start to answer questions about non-spherical stuff, but without going to the whole pain of the head-on collision.
Yes, we tried, but as far as I remember, this is the point in where we switched to cartoon, in the sense that even a single black hole,
even you didn't do what I'm asking in cartoon, right? If you did an axisymmetric non-spherical perturbation.
This we did not try yet. Okay. We tried in 3D, but even in 3D was completely impossible for the computational resources. Yeah, thank you.
On slide 15, I think you mentioned that you probably have more. So you have to, let's say, to evaluate your overall work, but more in terms of if they were electromagnetic or gravitational.
Yeah. Okay. So
I don't know if it was quasi-normal mode, if I understood that correctly, or
no. This is a time domain evolution of the perturbation equation.
Yeah. But so it probably before, but my point is, at some point you have to say, okay, these are more electromagnetic left.
Yeah.
These are more gravitational left.
Yeah.
Yeah. Okay. Thanks. Like in terms of how, did you get more electromagnetic or more gravitational? Like what was the recurrency of? I don't know if you remember that.
I don't know, to be honest. No,
This is okay. No, that's fine. It's fine. I think once you solve the system, is called time because the system is happening. Yeah. So both solutions are there. But
yes, but maybe there is one has a larger amplitude compared to the other, and I think he was asking for the ratio of the amplitudes between the two, but I don't remember.
In general, on the coupling, the parameter.
Yeah, for sure.
The radial charge.
Yes.
I'm working like this, and I know like the electromagnetic let's say, the amplitude is usually much bigger than the gravitational. That's what I was asking. Okay, but I'm not using the scale of let's say coupling.
Yeah.
It's just rational from usual. So that's what I was. But we can
Yeah. So then you show the nonlinear echoes.
Yeah.
So we see that there seems to be initially some echo.
Yeah.
But then in the later stage you don't see any echoes anymore.
Yeah.
So how can you be sure that initially there's really an echo and not maybe just an interference between different quantum modes that make this this dip in the amplitude also.
Yes, that's reasonable, but I mean, then how would you define an echo? Is in the sense that
I mean, before, I think in the linear case, you showed that there was a sequence of echoes, right?
well,
Yeah, a little bit like that.
Yeah.
So, but on the right plot, we don't see any of them.
well, actually, I don't know if it's visible, but you see there are two echoes here.
Yeah.
So more or less the same. It's less evident, but I think one of the reasons why this is less evident compared to this is the Chasm ratio. This is smaller, over 102, over 107. So
the thing is, I would be more convinced that really the echo was, if it was, so I don't know if it's possible, but to put the echo really further apart, so that you see sort of the ring down, then really bring down a lot, and then you see, then there comes a really loud echo.
Yeah, but this I think this is the point in the sense, since this is not a reflective surface, but this is just given by the potential cavity. Is the cavity that determines this profile here.
Oh, but maybe you can design the cavity in a way that it's later.
Yes, this has been done in another work by Guo and collaborator. They consider this sort of. They actually, if I remember correctly, they also went way closer to extremality to consider cases in which you have this behavior. I think he's. Where is it? Maybe it's easier this way. Yes, it's this works here. One collaborator, they have 2022. They consider this case and they show a clear behavior. But still, the point is that, I mean, apart from the fact that, I mean, the point is you need really to go very close to extremality to have a clear behavior. And yes, if you add a perturbation, if you want the configuration to be nonlinear, you are adding mass, so you are driving the system to smaller value of the Chasm-Mass ratio, and you go away for this beautiful configuration that gives you the more evident echoes. So it's a matter of tuning the parameter to find the best way possible. Yeah. I was wondering, what is the role played by choice of text? So you have some choices in it, citation, right? Yeah. But there is a couple of functions. Parameter choices. Does this function have a parameter that you can change? Well, in this case, we consider only the exponential choice, in which the coupling constant is alpha. For two reasons. First is the one, maybe the most popular choice that gives rise to spontaneous scalarization. So these scalarized profiles. And also is the one where double peak potential has been found. We tried searching other choices which satisfied the condition for spontaneous scalarization, but they do not provide double peak potential. So apparently we found this phenomenology only for this choice of decoupling. In general, for this kind of model, I would say there are two classes of coupling functions. The ones for which this condition is satisfied, so there is a causal solution such that the derivative is 0, which are the ones that generally can give rise, are suitable for giving rise to spontaneous scalarization behavior. So this phenomenon of tachyonic instability of the rise of mass from black hole and whatever. And the ones in which this is not the case, so they have a linear term in the scalar field if you want. And these are sometimes called Einstein-Maxwell dilaton model. And in this case, the Einstein solution is not a solution of the field equation. Because if this solution doesn't hold, then this is not a solution of the equation, and so the Einstein solution is not a solution. So these are two macro choices classes, let's say, of Chinese decoupling function, which are studied in this case.
So if I remember correctly, there was a paper about exotic compact objects and nonlinear effects. One by Sapienza.
Ah, okay, yes.
Yes. Is it related to echoes and nonlinearities like the find? Is it different?
It's actually different. In fact, they don't claim that they reveal echoes.
They don't claim that echoes are solved by nonlinearities.
No, they don't claim that they see actually an echoing behavior with multiple peaks, but they don't call them echoes because yes, the phenomenology is more complex. Really, these are boson stars, if I remember correctly, and claiming echoes in which you need an effective potential, a cavity, and whatever would be a lot more complicated. So actually, they don't do that, but they still see this behavior.
If you enjoyed the video, like and subscribe.